So good morning, everyone. I'm going to present the work putting consistency back into eventual consistency. This is joint work with Sérgio, Duarte, Carla, Ferreira, Rodrigo, Rodrigues, and my advisor, Nuno, Preguiça, from the University of Lisbon, and our collaborators from invariant-repair, Mahsa, Najafzadeh, and Marc, Shapiro. So nowadays, services are provided on a global scale. From small application that runs in your cell phones to huge social networks, more and more people are connected to the internet. And people are depending on these services on their daily routines more. For that reason, it's important to provide good quality of service to clients worldwide. A typical solution to provide low latency and high availability to clients is to use geo-replication. The idea of geo-replication is to collocate multiple copies of data with users worldwide so that they can execute operations on local data centers with low latency. However, the coordination between data centers still takes some time. And for this reason, programmers have avoided using strong consistency protocols to avoid coordinating in every step. However, giving up on the coordination imposes problems in the correctness of application. And that's what we are going to address in this presentation. So I want to give an example of a geo-replicated system that runs a weak consistency protocol. In our case, we consider causal consistency. In these systems, and we are modeling this application, a game application where we have players and tournaments, and you want to manage the participation of players in these tournaments and do matches and other operations. Here we have this. We want to impose this constraint that the player can only enroll in a tournament that exists. This is an instance of a referential integrity variant present in many applications. So in our system running causal consistency, Pac-Man will try to enroll in tournament A, so it submits the operation to the local data center. The operation executes locally with low latency, and Mario does the same in the remote data center. He enrolls in the tournament, and next, for some reason, Pac-Man tries to remove tournament A. It will execute this operation locally, and will remove any reference between any players and tournament A. But it will only do so for the references that it sees in the local data center. So after synchronization, both data centers will exchange the effects of the operations that each one executed. And in this situation, we will break the invariant of our application because we enrolled Mario in a tournament that no longer exists. The problem occurs because we are executing concurrent operations without knowing the effects of each other. So it would be impossible for the remove tournament operation to remove this relationship that was created when Mario enrolled in a tournament. The typical solution to solve this type of invariant violations is to use strong consistency. In this diagram, I'll show the interactions between the clients and data centers. In the bottom part of the slide, I'll show the ordering of the operations as they execute. So Pac-Man submits the operation to enroll in tournament A, and he submits that operation to the local data center. And in strong consistency, this data center will contact the remote data center before replying to the client. So that both data centers agree on the ordering for this operation. The data center replies, and now the same thing happens with Mario. Mario tries to enroll in the tournament, the operation synchronizes cross data center, paying the latency cost, and the operation is ordered after the previous enroll. When we execute the remove tournament operation, now we won't have the problem of not seeing references that were created between the players and the tournament, because all operations were executed in order. So the operation synchronizes, and the invariant is maintained after executing the operation. However, if you look at these operations, and we know the semantics of them, the enroll operations, actually, they don't conflict with each other, meaning that we could have executed these operations without explicitly coordinating them between data centers. We really need to coordinate is the remove tournament operation, when you want to make sure that when we execute this operation, there is no concurrent enroll operation in that when it executes. So ideally, we would like to reduce the coordination, and now I'm going to show how we will do this. So Pac-Man will try to execute the enroll operation to enroll in tournament A, he executes the operation, and now the data center replies immediately, because he knows that no remove tournament operation he executes. Mario does the same, and now we induced a partial order between these operations, allowing them to be executed concurrently and even out of order. When the remove tournament operation executes, now it's the time we have to coordinate between the two data centers, because we want to make sure that no enroll operation executes meanwhile. And in this step, we also collect any information about remote operations that enrolled any player in tournament A. So in this case, we also maintain the invariants, but we did not have to synchronize in every operation. We had the benefit of executing those two enroll operations concurrently in the local data center without paying the cost of coordinating among data centers. We propose a new consistency model called Explicit Consistency that will extract more information from applications to allow us to leverage these properties to avoid coordination in the general case. We also implement a system that provides explicit consistency, and we evaluate it in this, and we show the results in this presentation. We conclude with some final remarks about this work. So the definition of explicit consistency is actually quite simple. Given the information of the application correctness properties expressed in the form of invariants, you want to make sure that the system only allows the transition of states that maintain these invariants. Note that in comparison to other consistency models, we are not specifying any rules for the execution ordering of operation, allowing programmers to optimize and remove coordination when it's possible. We are going now to show how to concretize explicit consistency. And for that, we provide a methodology composed of 3 steps. The first step in our methodology is to identify I offenders. I offenders are sets of operations that, when executed concurrently, may break application invariants. The idea is to use a static analysis to go through the invariants of the application and the specification of it to identify these I offenders automatically. Knowing what operations cannot execute concurrently, so in our example, the remove tournament operation and the enroll operation, you deploy a reservation mechanism that allows the execution of these I offender operations avoiding coordination in the general case. I'll introduce reservations when we get to there. The last step of our methodology is to instrument the code to have the benefit of avoiding coordination in runtime. Unfortunately, we won't have time to cover the instrumentation in this presentation, but you can read more details about it on a paper. So let's see how the static analysis works and how we detect I offender operations. So the idea of the static analysis is to ask programmers to specify their applications. And we request them to specify two things. First, the invariant of the application. In our toy example, we only have this simple property that says that a player can only participate in an existing tournament. We are using first-order logic to express invariants in our prototype. So this expression can be the invariant can be expressed with a logical implication that says if a player P is enrolled in tournament T, it implies that variable P is a player and that variable T is a tournament. And we specify the set effects of the operations. So for the operations that we are considering, the enroll and remove tournament, the enroll operation will make the predicate enrolled PT true, and the remove tournament operation will make the predicate tournament false. The static analysis goes on by testing how these operations affect the invariant. So, considering an initial state where the invariant holds, we are going to simulate the execution of each of these operations. So consider that we execute the enroll PT operation, and we substitute the effect of that operation in the invariant expression. So our invariant, we have substituted the enrolled predicate by true. We do the same for the operation remove tournament, and we get the expression with the second part of the logical implication false. To see if these operations can execute concurrently without breaking the invariants, we combine the effects of both operations on the invariant. And in this case, we get an expression that says that true implies false. And we know that the logical expression of this value is equivalent to false. So we have broken the invariant, and found a pair of operations that, when executed concurrently, would break the correctness of the application. So this is one I-offender set. In practice, our algorithm, what we do is that we use a SMT solver to exhaustively search for every offending set in the application. You only require the programmer to specify the invariants of the application and the post conditions of the operations. The second part of the methodology is to execute these operations efficiently. And for that, we rely on this new mechanism that we've introduced called reservations. Reservations itself, they only have a very simple promise that we will execute I-offender operations without breaking the invariants. The design of these reservation mechanisms is, however, thought to reduce coordination in mind. So we provide different reservation mechanisms for different types of invariants. For instance, we adapt classical techniques of escrow to provide numerical invariants, such as those of the form x greater or equal than 0, like to maintain a stock of an item or to maintain the balance of an account. These are classical techniques that we use in our prototype. Actually, in the poster that I have, I show how we can use escrow, so I can show that afterwards to people that come to visit me in the poster session. But for this presentation, I will present the multi-level lock. The multi-level lock is another reservation mechanism that we provide that is general enough to provide any variant. So it's for any variant on the application, this mechanism works. And actually, it is the best mechanism that we found to implement, to provide referential integrity invariants, as the one in our example. So it suits best for this presentation. Also, we have other stuff, like the uniqueness in invariants, use specialized unique identifiers generator, or for instance, invariants on the range that we call range partition, that are those of the form of a calendar, where you don't want to put, don't allow users to assign events to the same time slot. We use something called a partition lock. More details on these reservation mechanisms are given in the paper. So the multi-level lock gets in a I-offender set and protects the execution of those operations with a lock. The lock will only allow execution of one operation at a time, but this operation can be executed by multiple clients in different locations. So coming up to the example, which is easier to explain how it works, we have the same information that we had before, but now we also store in the database the information what operations can execute at each moment. So the initial configuration allows both data center 1 and data center 2 to execute role operations in tournament A. Note that these role operations allow adding any player to that tournament. So in our example, when Pac-Man tries to enroll in tournament A, it executes the operation locally. The operation is executed without any problems. Mario does the same. They don't have to coordinate because they have the rights to execute this operation. And now we are going to see how our problematic operation goes on. So when Pac-Man tries to execute this operation, it will be forbidden because the local state of the lock does not allow him to execute a remove tournament operation. First, he has to ask the remote data center to stop executing role operations. He does so by sending a request for him to revoke his permission to execute roles operations. When the remote data center receives the message, he acknowledges the request and revokes his right to execute roles. Thereafter, the systems synchronize and the effects of these operations are propagated between the two data centers. So data center 2 will know that data center 1 will no longer execute role operations, but since we are enforcing causality, we also have propagated the relation between Mario and tournament A. So the system goes on, and now that he is the only one that has ownership on that lock, you will try to toggle the permission of this lock so that he can now execute the remove tournament operation. He issues a request locally, and it's of course satisfied because he was the last owner of the lock, multi-level lock. And now the application server can execute the operation remove tournament, and we make sure that all the relations were seen because we propagated them from the other data center, and not that no other data center will try to enroll any player in this tournament, leaving the database consistent afterwards. We implemented a system that provides explicit consistency. In fact, it's a middleware system that can run on top of many key value stores. We call this system Indigo, and Indigo only requires simple properties that are known to be efficient from the key value store. We are not going to cover these properties in detail, but to give an idea, we require transactions with weak semantics, and we also require causality, by the reason that I've shown in the example. Indigo is also extensible, so that programmers can provide new reservation mechanisms to provide efficient implementations for their invariants and maintain the correctness of the application. In the evaluation part, in our paper, we focus mainly in performance results and how are we successfully able to reduce the latency of operations, but we also evaluated the impact of using the reservations and how easy it is to use this methodology to implement applications. In this presentation, I will just cover performance-related results. So the deployment consists of 3 data centers. We used AWS for the purpose. We have one data center in Europe and 2 in the United States, 1 in each coast. And in each data center, n application servers connect to the local database. Clients submit operations to application servers in a closed loop. We compare the performance of our system against other consistency models that existing consistency models. We compare against causal consistency because it gives a baseline for the performance. We compare with strong consistency, which is a system that provides invariants, and we also compare our system against Red-Blue. Red-Blue combines previous consistency models, so when operations can execute without coordination, it uses causal consistency. When they don't, the system resorts to a strong consistency protocol. Explicit consistency further optimizes the execution of strong operations. So we implemented 2 applications. The first application is the ad service, and this application, the idea is that we want to enforce a global number of prints for each advertisement in an ad service platform. In this workload, every operation is an eye offender because we want to ensure that we don't exceed the bound of printing advertisements. We run the experiments with 1,000 advertisements, and this is the performance that we got. So Indigo performs comparably well similarly to causal consistency. We see the bottom bars, they are quite close. And in this case, because every operation is an eye offender, in the Red-Blue system has performance compared to strong consistency. In this application, we are using escrow. The second application is a tournament application from where we extracted the example that we've used in this presentation. The tournament application allows to add players, do matches, and other operations. We will detail the latency for each of these operations, but first, let's see the round numbers. So the workload is composed of 82% of read operations, and only 18% of operations are writes, which of those 4% do not require coordination. In this workload, our system still behaves quite well and performs similarly to causal consistency. We see that Red-Blue system starts to approach the performance of Indigo and causality. This is because most of operations don't need to check for the invariants. But let's take a closer look at the latency of each of these operations. So in this first part, these 3 operations are the operations that do not need to check for invariants. The view status operation, to disenroll a player from a tournament, and to add a new player from the system. We see that the only operation that takes more time to execute, the only system that takes more time to execute these operations is a strong consistency one, because it always has to coordinate all operations. In the case for the red-blue system and the Indigo, the performance is quite good and close to zero, the latency of operations. For the most popular operations in the workload that require checking the invariants, the enroll tournament and do match, we see now that red-blue has performance comparable to strong consistency, of course, because it has to check for the invariants, so it uses strong consistency, but Indigo doesn't, because it relies on the reservation mechanisms. The trade-off is the remove tournament operation, where Indigo shows higher latency than both alternative approaches. However, the problem with this operation is that we have to revoke the permissions to execute the other two operations. And this takes some time, but we haven't optimized the transference of reservations between data centers. So we believe that latency can go lower with engineering effort. So to conclude, explicit consistency successfully reduces coordination in the general case. We showed how to use simple programmer-provided annotations to identify the operations that conflict with themselves when executed concurrently. And knowing what operations cannot execute concurrently, we provide an efficient reservations mechanisms to allow the execution of those operations without breaking the invariants. We also shown from our evaluation that performance is comparable to causal consistency. This ends my presentation. I'll be like to take your questions. Thank you.
Nice talk, thank you. Can you provide more details about how simple these annotations are? So for example, do they involve quantifiers? How much manual work was it involved? And a second question is, do you know what's your false positive rate for the static analysis? So how many of these invariants you wouldn't have to enforce if you had more info?
Okay. So the first question? The annotations are really are quite simple. So we are using first-order logic to express them. I've shown quite early in the presentation. So this is the specification of the annotations is equivalent to this. We just have to annotate the code with the simple annotations that modify the predicates in the invariant. We are able to use global quantifiers and the existential quantifiers in these formulas. And about the false positives, so the analysis is conservative. So if you cannot determine if there will be a conflict, it will say there is a conflict. But from the applications that we've tested, we were able to detect the conflicts that we knew that exist in the applications. So.
Sorry, so you're saying you haven't seen any false positives? That's what you're saying?
Yes.
Okay. Interesting. Thank you.
Thanks. Thank you for the talk. So my question is, in your example about the tournament, you're adding players to the tournament, and then those are the operations that can happen without coordination, right? And then later you're removing a player from the tournament. And so the operations that can happen without coordination are monotonic updates, right? And the one that can happen, and the removal is a non-monotonic update. So I'm wondering if your system bakes in any knowledge of monotonicity.
We are not doing any analysis on monotonicity. We are just strict to the definition of invariants.
Okay.
So we see that updates the conflict.
Okay, so it's totally up to what invariant the programmer specifies, and your system doesn't have any knowledge of monotonicity?
Yes, we don't analyze monotonicity of operations.
Okay, thank you.
We have one more question right there.
Marcus Aguilera, VMware Research Group. I was wondering how you break your reservations when you have failures. I don't think timeouts or leases would work well in the wide area.
Well, so the idea of reservations. So yes, I moved a bit too far from the microphone. So the reservations are local to the data centers. They are not shared between the end clients.
Data center fails. What do you do with the reservations?
Yeah. Okay. So if there is some fail and the data center goes down, and we cannot use those reservations. But if there is a network partition and you cannot contact between two data centers, each data center still makes progress by using the local reservations that it holds. Of course, in the case of the example that I've shown, if someone wants to execute the remove operation, you won't be able to execute it until the data centers coordinate and exchange the lock for that operation.